Hey everybody, in this presentation we are going to learn how to take those three gas laws that we previously learned. Boyle's law, remember this one was that the pressure and volume were inversely related if the temperature and the amount of gas are held constant. We learned about Charles' law, where the volume was directly proportional to the temperature in Kelvin, as long as the pressure and the amount of gas were held constant. And we learned about Gay-Lussac's law, where the pressure was directly proportional to the Kelvin temperature, as long as the volume and the amount of gas were held constant. Now, in all three of those gas laws, there were two things being held constant and two things that were varying. But we're going to combine these three gas laws into something called the combined gas law. And in the combined gas law, only the amount of gas is held constant. There's only one constant. And the other three things that we previously had, the pressure, the volume, and the temperature, all of those are going to be able to change. So we're going to have more variables in today's problem. And we'll also go on and learn a little bit about something called Avogadro's principle. And yes, that does kind of relate to Avogadro's number that you learned in a previous unit. Now, the combined gas law, I need to just go back to having a pen and making sure I can write on here. The combined gas law, we take all of the previous laws, like we had this one. Think to yourself, what do you think this one is called? This is Boyle's law. And remember for this one, okay, moles, or like the amount of gas, and the temperature were constant. Then we had this gas law. Now think to yourself, what's this one called? And for that one, pressure and moles were constant. And then we had this gas law. Think to yourself, what's this one called? Think, what are the constants for this one? Remember, in this case, the volume and the moles were constant. Ugh, right back again. My ad is going to disappear again. What's going on with that? There we go. So do you notice that in each one of these, as I said on the previous slide, there are two constants and then two variables that are in the equation? Well, what if the amounts in moles is the only constant? Okay. What if that's the only thing that's constant? Well, what you can do is you can take these three equations and you can combine them into one big equation. And we'll see if I can get this written neatly here. Where the initial pressure, the initial volume, and the initial temperature are equal to the new pressure, new volume, divided by the new temperature. The only time that this is true is if the amount is constant. And this equation right here, it is known as the combined gas law because it is a combination of those three equations from above. Like, look here, P1V1 equals P2V2. Here it is right on the top. If temperature was constant and we crossed it out, we'd be left with Boyle's law. You could do that for every one of these. Like if you go back, and I'd have to totally redo all of this because it takes, of course, takes us down to everything. But if we go back, and I want to do this back in red, if you look at this again, what if the pressure was constant? Well, if you cross the pressure out on both sides, look what you have. Charles' law. And you could do the same thing. You could cross out the volume on each side if it was constant and be left with Gay-Lussac's law. So these three laws above combine to give us an equation that is known as the combined gas law, because it is the combination of Boyle's, Charles, and Gay-Lussac's law. Now, what we're going to do today is practice doing some calculations with this. As before, I don't know if you remember this from previous problems that you did, but the pressure can be in any unit as long as it's the same on both sides. The volume can be in any unit as long as it is the same on both sides. The temperature must be in Kelvin on both sides. So we're going to solve some problems using this equation and remembering that pressure 1 and 2 have to be in the same unit, volume 1 and 2 have to be in the same unit, and temperature 1 and 2 need to be in Kelvin. Okay, so if you take a look at this problem, I'll give you a minute to read it. When you are done reading it, you want to figure out what all of your variables are. Now, in every problem, 5 of those 6 variables should be listed in the problem. And then you're just solving for the one that is missing. So when I start to read this, a helium-filled balloon at sea level has a volume of 2.1 liters. Okay, do you see that? So the initial volume is 2.1 liters. Then you read on and you see where it says at 909 or 0.995 ATM. And I got to think to yourself, what kind of unit is ATM? Remember, that's atmospheres, and that is a pressure unit. So that is P1. And then going on, you see that it says it's 36 degrees Celsius. So that is a temperature. Now, the temperature always has to be in Kelvin. So we've got to take that 36 and we have to add 273. Do you remember that? Because that's the conversion from Celsius to Kelvin. And we get a temperature of 309 Kelvin. Now you keep reading the problem. If it is released and rises to an elevation at which the pressure, so here the pressure, there's the new pressure, 0.875 ATM. Now, one thing that works in our favor here is that, the two pressures are both in atmospheres. If one of them was in atmospheres and the other one was, let's say, in torr, we would need to change one of them to be in the unit, same unit as the other one. Okay, so that's something that's important to remember when you're solving problems. And it says here the temperature is 26. Again, you have to add the 273 because all of the temperatures have to be in Kelvin. So when you add 273 to 26, you get 299 Kelvin. And you can see here now that the missing number is V2. So what we're going to do is take our equation and we are going to solve, okay? We're going to solve for the V2. That's the one we want. We got to get rid of the other things. So we're going to cross multiply or divide both sides by P2 and multiply both sides by T2. So I'm going to multiply by T2 and divide by P2. You see over here, the T2's cancel, the P2's cancel, and you're just left with V2. V2 is equal to T2 P1 V1 over P2 T1. Now you need to put all of the numbers into it that you had up here into this equation and solve for V2. So V2, trouble with that today. V2 is equal to T2, 299 Kelvin, times P1, 0.995 atmospheres. Now you got to keep your ones and twos straight. That's definitely important. V1, 2.1 liters. On the bottom, we have P2, 0.875 atmospheres. And on the bottom, we have T1, 309 Kelvin. Now you want to check your units. Do you see how the Kelvin divides out and the atmospheres divide out? They cancel. And the only unit you're left with is liters. So that's going to be the unit on your answer. And wow, that's hard to see. So we'll just use liters. I'm going to have to write my answer up here because I ran out of room. To solve this on my calculator, I'm going to take 299 times 0.995 times 2.1, divide by 0.875, divide by 309. You multiply by all the numbers that are on the top, you divide by all the numbers that are on the bottom, and you should get the new volume of this balloon is 2.3 liters. The only thing that has stayed constant is how much helium is in the balloon. You can see the pressure went down, the temperature went down, and as a result of those two things, the volume went up to 2.3 liters. Now look at the next problem. Go through and read it and see if you can figure out all of these variables as you read it and which one we are solving for. So the pressure is 1 atmosphere and the temperature is 0 Celsius. So that's 273 Kelvin. And it says it occupies 30 milliliters. So that's the initial volume. Now the temperature goes up to 30, which is the same as 303 Kelvin. And the volume, it's put into a smaller container. And it says, what will be the gas pressure? So we're trying to solve for P2. So again, we have to take the combined gas law. And we got to solve for P2. I'm going to, on both sides, multiply by T2 over V2. Because my P2 will cancel, my V2 will cancel. And I'm left with P2 is equal to T2 P1 V1 over V2 T1. Now go ahead and plug the numbers in and get an answer. And you can pause the video here until you crunch your answer. Man, I'm having trouble here with this. Okay. There we go. So we need T2. We need P1. We need V1. On the bottom, we need V2. And on the bottom, we need T1. Now you can go through and cancel out the units that will divide out. And then you see you're left with APMs. Multiply by everything on the top. Divide by everything on the bottom. And you should get that the new pressure went up because the volume went down and the temperature went up. And both of those make pressure go up. So it went up significantly. Now, there's a name you've heard before. We're moving on here to Avogadro's principle. Okay. You probably remember Avogadro from the idea that Avogadro's number. 1 mole equals 6.02 times 10 to the 23rd particles. Okay. And there's a little bit of background in that. It was in the early 1800s that an Italian physicist named Amedeo Avogadro noticed that if he had equal volumes of gases at the same temperature, they would also be at the same pressure. And he surmised that if those three things, if these three things, P, V, and T, if there are all equal to one another, that the two different containers also, he said, have the same number of gas particles inside. Now, this was a novel idea. Like this is saying, like, if I have one balloon that is 3 liters and it's filled with helium, and I have another balloon that is 3 liters and it's filled with air, he's not saying they weigh the same. He's saying there's the same number of particles inside. Now, knowing what we know now, we understand, oh, well, that's why the air balloon weighs more than the helium balloon. Because if I have the same number of particles in both of those balloons, and they're both in the same room at the same pressure and temperature, the helium balloon would have to be lighter because its particles are lighter. Air is made of nitrogen and oxygen, and those particles, they weigh more. So that's why that balloon weighs more. But how many particles are in the balloons? That's what Avogadro said was equal. He, it was initially called his hypothesis. But for a second there, my computer locked up. I'm glad it didn't. But he was not the one that eventually determined this number. This was determined much later. And the other thing that was determined much later, like decades later, was that if you have a mole of gas, which is this many particles, that it will always take up 22.4 liters of space if you have standard temperature and standard pressure. Okay, so these measurements of all of this came later, but it's known as Avogadro's principle because he had the first idea that, hey, if we've got the same volume, pressure, and temperature, we have to have the same number of particles inside of that volume. And from that, we got this, that 1 mole of gas at STP, standard temperature and pressure, will occupy 22.4 liters. And this is great because this is true for any gas. It doesn't matter if it's a pure element like helium, if it's a compound like carbon dioxide, or if it's a mixture like air. Air has lots of different gases in it. If I have a mole, 6.022 times 10 to the 23rd particles, it will fill up 22.4 liters of space at STP. Now, that is really important. Standard pressure is 1 atmosphere, and standard temperature is 273 Kelvin. We're not talking about room temperature. Room temperature, we like our rooms more in the like 22 to 26 Celsius range, which is like 290 some Kelvin. This is actually the same as 0 degrees Celsius. Okay. Standard pressure. This is typical air pressure at, sea level. We're a little bit above sea level most of the time when we're in lab and we measure the air pressure, and for some of the labs that we would have done or will do. When we measure the air pressure around Dallastown, Pennsylvania, it's usually like 99 kilopascals, which is a little under normal. Remember, 1 atmosphere is the same as 101.325 kilopascals. It's the same as 760 torr or millimeters of mercury. Do you remember that? These are all equal to each other. So that's at standard conditions. This is true. And that gives us something we can then use to solve some problems. Like here's another problem, right? Now this says if a mole of gas at STP has a volume of 22.4 liters. Sometimes students miss that this is actually giving you 2 numbers. It's giving you P1 and T1. We just saw on the other slide that these are the conditions of STP. And it says that at STP, it's 22.4 liters. Now, this is more what a typical room is like, 25 Celsius. So that's T2. Let's see, we have to add 273, so that's about 298 Kelvin. It's about what temperature I like my rooms, 298 Kelvin. Now the pressure, notice the kilopascals, it's a pressure unit. We either have to convert this number to atmospheres, or we have to convert the atmospheres to kilopascals. So I'll do a quick conversion. We know there's 101.325 kilopascals in an atmosphere. Do you remember using factor label to change your... So the kilopascals will cancel, and I take 99 divided by 101.325. Now I get a very long number, but I am going to just round that off to 3 sig figs, 0.977 atmospheres. So it's a little under standard. But the temperature went up a good bit. 25 is, a good bit higher than standard 0. And we're looking for what's the volume. So we have to solve. So go ahead and try to rearrange that. Solve for the volume, V2. And you can pause. I'm going to multiply both sides by T2 over V2. That way over here, they cancel, and the only thing I'm left with is, the P2. So P2 is going to be equal to, I have to put in T2, 290 Kelvin, times P1, 1 atmosphere, times V1, 22.4, over V2. What did I write V2? Oh my goodness. You know what? This just shows you how. Look, I'm going to erase all this. And most of it is going to be true. Look what I did. I had to solve them for P2. We knew P2. So I got to erase this side too. Hold on. And see, that just shows you we all goof sometimes, don't we? P2, V2 over T2. How many of you were thinking, what in the heck is she doing? As if you were. Well done. All right. So my mind must have wondered. I want to solve for V2. So I've got to do T2 over P2. T2 over P2. And I go back and I can cancel out the P2 and the P2. Now we're cooking. V2 is equal to T2 P1 V1 over P2 T1. So T2, 298 Kelvin. P1, 1 atmosphere. V1, 22.4 liters. P2, 0.977 atmospheres. T1, 273 Kelvin. Now I can go back through and get rid of things that cancel, like the Kelvin and the atmospheres. And then I want to multiply by everything on the top. 298 times 22.4. I want to divide by what's on the bottom, 0.977, and divide by 273. And I got for my new volume 25 liters. So 25 liters of air in the typical room is a mole of gas. So 25 liters of air in a typical room, that is what contains 6.02 times 10 to the 23rd particles. So you've got lots of examples of how to solve this, and even examples of what not to do there, because I had to erase. Another way, though, that you can use this little piece of knowledge, did we somehow end up with, no, there we go. I was going to say I couldn't get it to advance. We can do simple problems like this one. And this is going back to the factor label that you learned right near the beginning of this second trimester. Now, there's a lot of things that you've learned this year. that are going to go into solving what looks like and is actually a pretty simple problem, but you learned a lot this year. First of all, carbon dioxide. Jeez. I forgot that I was not in like a pen mode, so I thought it was. So first of all, carbon dioxide. We have to know what that is. Carbon is C, dioxide O2. So many of you probably already knew that. Then we have to think, what do we know about carbon dioxide? Well, we can get its molar mass, like how many grams are in a mole. Do you remember how to do those problems? Look on the periodic table. Carbon weighs 12. There's 2 oxygens, and you look on the periodic table, and oxygen weighs 16. So we multiply that by 2 since there's 2 of them. And the total mass is 44 grams, equal to 1 mole of the gas, carbon dioxide. Now, if I had a different gas, this problem would have been different, and this number would have been different. You remember that from earlier units. But we just learned that it doesn't matter what gas it is, that a mole of gas is equal to 22.4 liters of space. And these two things, these are factors that we can use in our conversion, sort of like how we've used things like, hey, a foot is equal to 12 inches. And remember when we did factor label earlier, we'd start with what we know. We know this is a liter. And then we start setting up factors. We know that 22.4 liters is equal to a mole of CO2. And the reason we put the liters on the bottom is so that it will divide out. Now the question doesn't say how many moles, it says how many grams, so we need another step to go from moles of CO2 to grams of CO2. And we added up that molar mass. So we know that it's 44 grams in 1 mole. And now looking at that, the moles divide out, and I'm left with grams of CO2 for my label. I take 1 divided by 22.4, I multiply by the 44. I got 1.96. I'm going to round it to 2 sig figs. So I originally got 1.96, but I'm going to round it off to 2 sig figs and just make it 2 grams of CO2. Go ahead and try this one as also a factor label. Maybe start by writing down, what things do you need to know? Like you need to know that 1 mole of gas is 22.4 liters. And you can only use that because this is a gas. What else do you need to know conversion-wise to solve this problem? That's right. You need to know the molar mass of hydrogen. That's an easy one. H2. Hydrogen weighs 1, so a mole weighs 2 grams. Did you notice here we want the volume in milliliters? We need to know the equivalency between a milliliter and a liter. Do you remember that from earlier in the year? A milliliter is 1/1000th, or 0.001 of a liter. Once you have that, start with the number you're given and start setting up a problem. We eventually want milliliters. We're going to have to convert from grams to moles, moles to liters, and then liters to milliliters. Two grams in a mole. I just used that conversion right there. A mole is 22.4 liters. I'll just use that conversion. And a milliliter is 0.001 liters. I just used that conversion. And if you look, the grams cancel, the moles cancel, the liters cancel. Everywhere in here, the top and bottom of the factor are equal to each other. So we take this number, plug it in, divide by 2, times it by 22.4, divide by 0.001. And I got 103 milliliters of hydrogen. Now, I hope that through doing this, you saw how you could do the combined gas law to solve problems. That was this one. And then how you could use Avogadro's principle. And the one problem, they were the P1 and the T1 and the V1. Or you can use that in our conversions, knowing that 1 mole of gas is 22.4 liters. That's if it's at STP. Now, we're going to give you practice problems to try. Remember, things need to be in units that match, like P1 and P2, V1 and V2. Temperatures have to be in Kelvin. And remember, when you're doing your factor label problems, do like we did on that last page. Always match up your units so that they divide out. And multiplying by what's on the top and dividing by what's on the bottom to get your answer. I hope learning about these equations and quantities helps you solve some gas law problems. Good luck.